Alright, so continuing on with our next one. We're now going to go ahead and kind of focus on concentricity and what that geometric tolerance means. Now, just give you a brief idea of what it deals with. Concentricity, find some white space here, deals with concentric, make that red, concentric features such as, or cocenter, I should say, that's a better way to word it there, meaning that a center axis or a center point would work for an example here. And we have a nice little example on this page for concentricity. See it right there. I'll give us a quick zoom in and what it means. Let's take this example right here. Here is the call out. Here you have a cylinder with another cylinder. It's got like a little O-ring groove in it. And here is the feature control frame that shows, first of all, the symbol. We look back in the text and we find out what that symbol is. And that symbol, of course, stands for concentricity. Circle in a circle. That can be found on page 559. So that's our step one. All right, this is a concentricity geometric tolerance. Now, our zone of tolerance, diameter 0.1, with reference to geometric datum feature A. So we check datum feature A, right here it is, and it, by this arrow, tells us that it is related to the overall feature of this cylinder. Now, by the fact that let me undo a little bit of that so we can see a little clearer. The fact that this geometric feature, I'll zoom in on it some more here. The fact that this geometric datum feature, this datum list, attaches to this line. See how the triangle attaches to it right there? Because it attaches to this dimension, or this extension line of this dimension, it means that it is referencing whatever the dimension is referencing. Well, the dimension itself is referencing this overall cylinder. So it says, okay, datum A here is the overall cylinder that this dimension represents. So, another way of saying it would be that this is datum A. That would be the equivalent of doing this. Works the same way. So anyway, we have now determined that this feature control frame calls out a concentric geometric tolerance. This is our zone of tolerance, and this is the feature we are referencing from. It doesn't mean that we are giving a geometric tolerance to this feature. No, we are referencing it. The fact that this feature control frame is attached to this dimension means that it is related to this dimension, or whatever this dimension relates to. This dimension relates to this cylinder, so this cylinder is the one we're actually applying the geometric tolerance to. Okay? Now let's carry on over to this side and kind of see what it means. This is the equivalent way of saying it. A lists the surface, lists the feature that we're referencing, and it says concentric to A within diameter 0.1. It's saying the exact same thing as shown to its left. So A and B, as you see in these figures, mean the same. Now, here's what it means. It means that, zoom in just a bit. Let's zoom in real close here. If I draw a circle right here that is centered on the center line for this cylinder, its diameter right here is 0.1. If I draw a tolerance zone of that diameter, the center for this feature has to fall within that zone. Let me draw it over here. Here's the cylinder we're using for reference. This is cylinder A. It's the same thing as drawing it this way. Here's the yellow cylinder that we're actually applying the tolerance to. And let me undo that one. I could also do it this way. Zero, 1, I think it is, and A. I first find the center of the big cylinder and I draw a diameter of 0.01. That is right, isn't it? Let me make sure I'm right on that one. No, it's 0.1, sorry. 0.1. I draw, let's make it blue here for us. I draw a zone that is 0.01 diameter wide, and the tolerance says that anything that the center line of this cylinder has to fall within this zone. Right now it's good. However, if it was out here, the center of that, it would be off. Let's take a look at this sketch here. See, here's an example of what you couldn't accept. Like if a part came out this way, you couldn't accept it. It would be rejected. Because look, here's the zone that's allowed. Yet here is the center line of the overall cylinder. See how it passes out right there and there? That means it fails the geometric tolerance. If the cylinder center line were to lie in here, like right there, that would pass. But by the fact it sticks out, it fails. Now, of course, you might say, well, as far as it's actually in there, whoops, didn't mean to do that. You could say that it does actually keep for one part there, since it actually does fall within, but you get the point. In our own little sketch, it's the equivalent of doing this right here. Here's the secondary cylinder. Here's the cylinder we're actually interested in. Here's the cylinder we're using as a reference. And we're just going to warp it just enough so that the center line is that way. Here is my zone of 0.01. And therefore we can see that it fails. Of course, the 0.01 is centered on the actual diameter of A, which is this one. This is A. So hopefully you kind of figured that one out. Let me give you another example. Let's say I have this situation right here. Here's cylinder 1 is attached to cylinder 3, and this is attached to cylinder 2. Okay, now let's say I want to apply a geometric tolerance to number 2. This is the one I want to apply it to number 2 with relation to number 1. Kind of like the last problem. And let's be specific. Okay, so that's where I want to apply the tolerance. And I want to use a cocentricity. Well, step 1 is to identify which one of these cylinders is the datum. Okay, so I will say that cylinder 1 is the datum by doing this. That is one way to represent it. Then I will point out that I have a feature control frame, and here's a neat point. Feature control frames always start with the symbol on the left. I'll draw the symbol for cocentricity. I'll give the diameter value, we'll say 0.2. And I need to reference which datum I'm using as reference. So, of course, it's A. And then I draw a little leader. Now notice this is a leader, whereas a datum reference is a triangle, backwards triangle. Keep that in mind. Therefore, I'm saying that with relation to datum A, which is the cylinder, right here, I'm creating a diameter of 0.2. So if this is the center line of this diameter, I will draw a circle that is diameter of 0.2. I will draw a zone based off that center point. And the center line in cylinder 2 must fall within this line to pass inspection. And in my case of the drawing, it does. Now, the fact is that in real life somebody is going to test this. They're not actually going to draw all these little zones and everything out. They are going to draw this and this, but they're going to use that information to test it in real life. No one's actually going to draw out this little circle. They may create some molds or testing devices to do it, but it's just the concept that we're working on. So this you create, but they check all this stuff. That's what they check. In real life, in physical reality. They take the physical part and check that based off your prints. So that's cocentricity. And that, unfortunately, is just one of many, I shouldn't say unfortunately, it's just one of many that we're going to learn as we move along. Now, if you're having a hard time with this whole projected zone thing, let's take a look at this figure 1623 right here. Okay? Now, we have figures A, B, and C. A identifies a datum, which is the surface right there. The feature control frame references datum A and datum B, which we don't really see datum B just yet. The feature control frame also has a couple of modifying symbols, has a most material condition here, and provides a diameter zone of 0.25. Okay. Well, in this particular case, the geometric tolerance is of position. We can tell by that symbol there. And what you see right here in B is a portion of the projected zone. It's only half of it. The other side is the other half of the projector zone. It's not even shown. Okay? And what you see in C is a deviation that still falls within the projected zone. So if I were going to take some measurements, I would see that the distance from here, since it's only half the zone, would be 0.125. The other half would be the other 0.125, and therefore we would be a total of, if it were there, 0.25. Okay? That's what the projected zone is. It's just a zone, usually a diameter value, to establish a certain width based off another feature. Okay? Now, while we're here, we'll take a look at the other geometric tolerance on this page, the one called symmetry. And we're going to take a look at figure 1626 for reference of it. So that's on the next page. Actually, it's 2 pages over. There you go. Symmetry. Now, symmetry deals with something being symmetrical to another feature. So, for example, with the geometric features or geometric feature control frame, we're going to be referencing some other feature. So we look at here, what's the primary? Well, datum B seems to be the primary. Now, figure B shows us what this exact same callout would mean if we were to write it out. We do see that B, datum B, is represented on the side view as the base for this feature, symmetric. Okay? So this back surface of this object is the referencing datum. Keep that in mind. Now, precision tolerance is the symbol we're given, and the zone is 0.08. So let's take a look at the reality of it right here. First off, we see our tolerance zone. Note the value. It is 0.08 wide, so the distance from here to here is 0.08. That's pretty understandable. And also note that the tolerance check in this case, this is exaggerated of course, but it's showing that a line of symmetry must lie within that zone for this feature for this to be correct. Now keep in mind they always exaggerate deviation just to explain it. It's usually not going to show up that bad. If it did, it would be way outside. But they're helping you understand what you're checking. Okay? So it has to be within symmetrical proportion to two datums in this case, because you'll notice that the callout showed datums B and A, primary and tertiary. So symmetry is established from here to here, and also from here and here. Okay? So that's symmetry. Alright, so now we're moving on to a different type of set of tolerances. And we are now talking about form tolerances. Tolerances that aren't so specific on a particular, position or location, but more dealing with the actual shape of the part, of like straightness, and here's some good words: straightness, flatness, circularity, or roundness, that's what they mean by circularity, and cylindricity. And a form tolerance, of course, specifies a tolerance zone that the particular feature must lie in. So we're going to be dealing with surfaces being flat, being circular, being straight. That's what we're going to deal with form tolerances. But they're pretty much handled the same way that the other ones are. They just have different symbols and a few different meanings, but not too much that's too tricky for you. We'll start off with straightness. And we're going to reference figures 1627. So let's take a look at that on the next page, 1627 for straightness. Alright, here is the geometric callout. Notice that they don't provide a datum reference. Well, why not? Do they have to? Not necessarily, especially for form tolerances. It's just a given. You can actually reference the actual surface for being straight, because straightness is just straight. It's either straight or it's not. The actual interpretation of this callout, and first of all, keep in mind that's the symbol for straightness. There's your tolerance zone. You don't need a datum. Look what it means. There is the tolerance zone that is 0.01 wide. We'll zoom in some more on this. We've got the 0.01 wide zone, and you can see a deviation of the part in the fact that it's not really straight in reality, and most parts aren't perfectly straight, but it does fall within the 0.01 tolerance zone for being straight, and therefore is okay. So that's all it is just set up a tolerance zone and compare it to straight. And some parts do this in them. They have some rough spots, but as long, of course this is a very large version, but as long as they fall within that tolerance zone, they're safe. If they deviate outside that tolerance zone, then you have failure. Okay, there's the concept. That's supposed to be a part surface. Sorry if it looks funky. But a straightness tolerance is not too big of a deal. You can pretty much understand that without too much problem. Circularity is kind of the same thing, dealing with cylinders. Of course, if you look at it real closely, it says circularity. It describes the distance from the axis of all elements of a revolved surface that is intersected by any plane. It's a great way of just saying this right here. Notice again, you don't actually have to have a datum. You can just point at the surface and say, hey, this surface here has to have circularity. I'm sorry, I didn't mean, this is not the circularity. This one's actually flatness. But, we can talk about the same thing. I've just been telling you what circularity was based off a flatness tolerance. But while we're at it, why don't we talk about it? You'll notice that a flatness is pretty much the same as, or very, very close to, the concept of a straightness tolerance. Flatness symbol, region or zone, tolerance zone is there, and the same procedure is true. There is your zone of 0.01 wide. You see the part fluctuating in its flatness. It's not perfectly flat, but you know what? It's flat enough that it fits within that zone and therefore passes a reality check. Now, if you had a zone like this, and your part was doing this little number, to be fine, but if it did this along one of the surfaces or another, it would fail. And that's all it is. And this is going to be one of those things that can be on any surface. all the way around or just on one surface in particular. For example, if a part has another object lined up with it that need to slide back and forth, you would want probably some kind of tolerance to control that, because you don't want rough surfaces. Okay, now let's talk about circularity. Circularity is shown on the next figure. Just jumped the gun on that one. There we go. Circularity, shown on this figure, deals all the way around an object, but it's kind of shown the same way. And you can probably get a concept too. Here's your symbol. There's your tolerance zone. Again, you don't need a datum. You're just referencing a form or a surface. There's the call out. And if you were to take a section view of the part and kind of look at it, like here's my section, section AA, there's the result. I draw a tolerance zone. A tolerance zone would be like this, where this right here is the 0.025 wide. You draw my tolerance zone here, and even if my part is shaped like this, it's not perfectly cylinder, but as long as it falls within this zone, as this part does, it passes. Because in reality, you don't really have a perfect cylinder. You have little deviations like this, and little ups and downs, and little rough spots. But as long as those rough spots and those deviations fit within that zone, it's okay. Circularity, controlled with cylinders. Now, since the cylinder itself can be something like a cone, you see here, you don't have any major differential. You can still have the same feature control frame and same values associated with it. However, in a cone, you're going to have to check it at different points. And of course, the cross section is still the same, but you may do multiple cross sections if you were testing it. All right? Because the circular zone that is created for testing is simply based off what the perfect is supposed to be. For example, if it's supposed to be a value of 0.9 right here, we would draw the 0.9 perfect circle, then create the tolerance zone around that, splitting the difference. We would offset 0.125 to each side, and does the part fall within that? If it does, it passes. So it's pretty much the same thing if the cylinder or a cone, doesn't matter too much. Now here's a good example. What if you're dealing with a sphere, like just a ball, a real life ball, and you're checking it for circularity? Well, no big deal. Now I do want to draw some attention here. Notice that this feature control frame doesn't have an arrow. It's just simply under an existing dimension. Like for example, this is the dimension of the sphere, and it says it's a sphere. You see the S there, that's a sphere, diameter of 25 plus or minus 0.4. So that dimension's there for somebody to make it. This geometric tolerance is below it just to say, hey, not only are we saying make it this, but we're applying a geometric tolerance. Notice that we can have regular tolerances and geometric tolerances coexist. And we take the cylinder and we check it. And somebody comes along, they do, set up some kind of form, and they again have the tolerance zone that fits around what the circle is supposed to be, or is based around what the circle is supposed to be, and does the sphere stay within it? That's all you gotta prove. So cylinders, cones, spheres, doesn't matter, circularity can be tested for each. Now let's take a look at cylindricity. I can't say it, never mind. Anyway, hope you found that attempt humorous. Cylindricity is not that different in appearance than that of concentrics. In that you take, of course, again, they do show it where it's just an add-on to an existing dimension. There's your symbol, there's your tolerance zone, and here's what happens in reality. It, however, is not based off over the perfect cylinder, but an equal distance, like, for example, the tolerance zone center is based off an equal distance from the axis. Okay? So if this tolerance zone is 0.25 wide, then we would draw the correct value of what the cylinder is supposed the center line from here to what the perfect cylinder is, and then we would create the 0.25 based off that. And we just check the cylinder. Now you'll notice the cylinder check is not based off of a section view. It's based off of a continuous evaluation of the overall surface of the cylinder. And that's a significant difference. It checks the entire cylinder, not just at points. It's checking it from a side view or a side concept. This would be to keep a cylinder from getting too big and maybe not fitting in a shaft or something, or being too small and being loose. Again, not that much difference except in concept of where it's checked. Now we move on to the other type of tolerance. That's the profile tolerance. And we can read a little bit about it real quick. Profile tolerance is an outline of an object. The element's profile consists of straight lines and curved lines. So basically, a profile is the outline. Again, not too dissimilar for some of the things we have been talking about. We have a great little example over on the right here. We have an object that has some type of curved surface to it. And so we establish a checking zone, a profile zone, and we check it to make sure it fits with its actual shape, fits within that correct profile zone. If it does, it passes. If it doesn't, it doesn't. Do note that profile tolerance zones indicate how far from the basic dimension a surface can vary. Profile tolerances can be bilateral or unilateral. Let's take a look at a good example. Next page. Here we have a part with a lot of basic dimensions on it. Notice this. Remember, box means basic. Here we have a feature control frame. It has a symbol in it. We check and see what that symbol is. We would flip back in our book and we would check and say, yep, that's a profile tolerance. It's profile of a surface symbol. Then we check and see what our tolerance zone is, and we also reference in what datum feature we're looking at. A, B, and C, primary, secondary, and tertiary. So we find those. There's D, there's C, there's A, and there's B. B references the bottom feature, the bottom surface of this part. A references the back side. See, this is a side view, so it's the side on the back there. C references this surface. So we are checking the overall profile shape in comparison from these features, from the back, from the bottom, and from that C surface. So let's kind of see a little bit more about it. Okay. Here's the interpretation. There's the 0.25 wide tolerance zone. It's referencing it from B. It's also referencing it from A, as you see there, making sure it falls in. Again, these are all based off of basic dimensions. We would set up what the correct true size should be based off all these basic dimensions, and then we would check to see how far off ours is, our actual made part. Again, it's not done in drawing, it's done in reality. The part is checked in reality from the perfect, which would be considered, this, and the true, or the actual. So hopefully you're kind of getting a feel in some of this. One last little thought. Do note that when you want a profile to be checked all around the part, just throw in the all around symbol. It's typical when used with welding and also here. So now we're going to talk about angularity tolerance, parallelism, everything, and perpendicularity. And we'll just go through and kind of check them here real fast. Shouldn't be too much. You should be getting the hang of it by now a little bit. Here we have angularity. Here's our object. Here is a particular surface we're interested in, or feature. We have a symbol, we have a datum, and we have a value. That's interesting. Notice that the value is provided after the datum. Let's check it out. Here's surface A. We see how it's referencing this line, which means it is referencing everything along that bottom surface. So the bottom surface of the part is our datum. We're saying that there is a basic 30 degrees supposed to be there, and we're going to step a tolerance zone based off that 30 and say that surface has to fall within it. And of course, down here below is our interpretation. Deviations in the surface may occur, but as long as they don't occur outside that zone of that perfect 30, we are good to go. Now you'll notice that it's a 0.05 wide tolerance zone undo that, as was specified, but you'll notice it's not a diameter value. Notice that it doesn't center itself around that. It's just to one side. And that's one thing to know the difference. When you don't see a diameter in front of a value, it means it's just from the perfect to one side. Which technically you could say it's the other side, but we're going to increase it. We're going to say this is your target zone that's allowed. Okay? That's angularity, based off surfaces that have an incline or an angle associated with them. Not too tricky. Let's take a look at the other one. Here we're checking out parallelism. Here's our drawing. Drawing has a feature or a datum symbol right here referencing this bottom surface. Here's our feature control frame. We say A is our datum. Okay, check that. This is our parallelism symbol, and this is our zone. So we check it. There's our datum plane. We have the zone 0.1 wide of what it's supposed to be. And then we check and see if our surface falls within it. Of course, in this little picture, it does. So it would pass. This can be based off anything. Now, another one that's coming up is perpendicularity, which is a very, very popular one, which controls a lot of things. It does point out that parallelism, there's another little diagram of parallelism that you can check out there. But let's talk about perpendicularity. Okay, here's the symbol. It is referencing this surface. Could it have been shown by this? Could they have done this and done the exact same thing? Absolutely, that would have worked too. However, there's nothing wrong with the way they've done it either. Get rid of some of that. Okay. So, datum feature means this is our datum. This is what we're looking at for a baseline choice. We've got the perpendicularity symbol. We've got our tolerance zone. We've got a reference feature. And it basically means that this surface right here must be perpendicular, 90 degrees from this bottom surface within a specified tolerance zone. So we check out the result. And interpretation, here it is. If this thing is slanted, that's okay, as long as it stays within that zone from true perpendicular. Pretty easy to understand, and perpendicularity is used a lot. You do have to have a surface that you consider to be the perpendicular base, and then you establish a perfect value and your zone based off that perfect value. And make sure it falls in it. You'll see perpendicularity a lot. So let's do a quick example, kind of make sure that we're getting the hang of some of this stuff. I'll create some more space. Well, no, I won't create too much more space. It looks like we're out of it. I'll make another set of notes. All right. Let's have some test runs just to make sure we're getting it down pat. Here's an object. This object has surface 1, surface 2, surface 3, surface 4. Let's say surface 4 is the critical surface. That's the one I want to check. Now, what are my options? If I want to use perpendicularity as an option, what surfaces can I use as my datum or base reference? Well, hopefully you said either surface 1 or surface 3. Can't use surface 2 because it's not ever going to be perpendicular. You could use parallelism if you wanted to, but you can't use perpendicular. So anyway, with that in mind, let's do a quick bit of erasing there so I can actually see something. Get rid of that, that, and that. There we go. So, we need to identify our datum. Here are some options. Which one is more correct? Option 1 or option 2? Well, the answer is neither is more correct. Both work just fine. So we'll just keep them both. Now, what do I need to do with this side number 4? Well, I need to add a feature control frame. A couple ways I could do it. I could do it like this. I could do it like this. I could do it like, let's see, how else I could do it. I could do it, I don't have enough room, let me erase something. I could also do it like this. Here's a dimension. I can also do it like that. Any one of those works. I personally like just adding them with a nice little leader like this one and being done with it. Okay? So with that in mind, I'm going to erase the other stuff just to kind of clear the screen. And I'll keep that one. I just like the little leaders and things. It's just my thing. So, you know, I'll give myself a little bit more space in the feature control frame. Now, feature control frame. 3 boxes. Let's start with the back. Since we are referencing a surface A, or datum A is our surface, we're obviously going to put this with A. And keep in mind, I'm adding a perpendicularity geometric tolerance. So I need to add the perpendicularity symbol. And I need a value. So I can use a diameter value, or I could use just a zone, and it can be any value for this at this point. We'll just say 0.1. What that means is that I'm going to draw a line that would be, in theoretical, I would draw a theoretical line that is perfectly 90 degrees from the bottom surface, draw my zone around it, and then check and see if it falls within place. If it does or it doesn't, that's the choice. Okay? So that would be a legitimate perpendicularity geometric tolerance for this application. Now, let's try another one. Remember, this is surface 1, 2, 3. We'll switch it up a little bit. And now, let's add a parallel. Let's say, okay, I want surface 2 to be parallel with surface A within a tolerance. Well, here's a quick way to do it. Think about what I'm going to put in here. What am I going to put in this last box right here? What's going to be in this? Well, that's correct, A. What's going to be in this box? The parallel symbol. Okay. And what's going to be in this one? The actual value, which can be any value for this point. We'll use 0.1 because that's a good value. There we go. It references A and its surface. Let's just say for kicks and giggles, I want to add another parallel into surface 1. So obviously now I've got a problem, because surface 1 cannot be parallel with A, so I need to do what? I need to add another feature control, or I need to add another datum reference. So here's what I'm going to do. I'm going to draw a B right here, a little arrow to it, or a little leader line, backward filled in triangle, and there we go. Now I can say bam, 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 parallel 0.01, and B is my datum reference. There we go. So really, when you just break it down and don't see all the symbols and jargon all over the place, it makes it a lot simpler for a person to kind of understand. Alright, well, we're going to stop the video now for a second, just do some checking up, let the computer cool down a bit, and we'll pick up in another one. See you soon.